Howdy everybody in YouTube land. And you could tell by the beginning of this video that this video is going to be about the WeatherSTAR Jr. These particular machines were kind of bespoke in a way that the WeatherSTAR 4000 was the primary star that was in service at the time that this was released. This was released in the mid-90s. The 3000 in the earlier versions, the Star 1 and the Star 2 were all upgraded to 3000s to move the data carrier over to subcarrier instead of using the vertical blanking interval. The trouble is, this kind of, I guess this was targeted more towards smaller network operators, MSOs, or back in those days, you could actually subscribe to TWC as a end user and purchase a video cipher receiver, and they would give you one of these. So if you wanted TWC by itself in like a small apartment or a small venue, campground, very small town, something like that, this kind of filled that market. I'm assuming they did this on purpose because of you had to purchase these as the network operator yourself. These weren't rented devices. Because if they were rented, they would send you the latest and greatest, which at the time would have been a 4000. So that's my only thing that I can think of, and it's my opinion on this matter. But anyways, so this is the Junior. It basically mimics the 3000 and actually uses the 3000 data stream. Difference being it's a much smaller unit, much newer than a 3000, and it doesn't have all the same features. For example, this does not handle audio. This only handles video and warnings. Even warning sounds, you had to have an external tone generator to do warnings, which I can take a look at that later in this video. So this is serial number 101259. There's actually two versions of these. There was ones that began with 1, like this one, and there was ones that began with 2. And they're two different versions. They had two different versions of this unit. And this was the one that I reverse engineered. And there's wires soldered on and hanging out the back of it and things like that because I had to figure out how this thing worked. And actually, it took someone loaning me a 3000 to unlock the entire secret of this machine because of how the data is handled. But anyways, so this is version 1. And this uses a rather unique processor. The TMS 34010 runs at 40 megahertz. So this thing is much faster and more capable than that of the 4000, but it only had the 3000 graphics package, and that's because it is limited on the output side and storage, because this is the RAM, and that's the only RAM you got. I'm not sure how much RAM is there. I think there's only 2 megabytes or something like that. I'll have to look that up, but there's the chip. This is dual port memory. And this is the main system RAM. It's actually SRAM, and it's battery backed. So when the data gets downloaded from the satellite from this port right here, which is the subcarrier input, the information stored into these chips, and this is the supercapacitor. This is not a battery, my bad. This is a supercapacitor that keeps the memory. So if the power is unplugged and plugged back in, it'll return back to normal programming. Unless the data expires. If it's been an hour or something like that, it will wipe out all the data naturally. But anyways, so this uses a TMS 34010, which is a very strange processor. They were popular in arcade machines, some arcade machines, and they were also popular on graphics cards at the time period because not only is that a CPU, but it's also a GPU. It has graphics opcodes built into the CPU, so you can perform graphics calls from within the chip. So it was kind of one of those weird things that it can execute code on its own, but it also has a bus interface on the outside world, so you can interface that with a host processor. But in the case of this unit here, Wegener, which is the company, Wegener Communications, designed this receiver in collaboration with TWC. They decided to use that processor as a host processor. So the other unique thing about that processor is it's a bit addressable processor. So the address space, when you're let's say pretend at the top of the address you got address 4000. Let's say if it's address 4000. Well, 4000 is the first bit of 16 bits of that chip. 4001 would be the second bit. 4002 would be the third bit, all the way up to 4016. So 4017 would be the next bit, and the next after the first 16 bits. So that's 2 bytes. So every 2 bytes, it would move 2 bytes on the address bus, but it would be, it's weird. It's hard. I don't even understand it all the way. But the other problem with these, especially when it comes to reverse engineering, because I tried to take a look at these ROMs and study the design of those ROMs, and it's kind of hard doing it because the debugging reverse engineering tools for this particular chip is kind of hard to find. And if you're looking at a hex dump on your computer screen of the firmware, it doesn't coincide with, say, the disassembly. For example, this processor is supported in MAME, which has a disassembler function. It had to be fixed. I reported a bug about over a year ago, and they fixed it. But when you're looking at the disassembly and you're looking at data references, when you go to the hex workshop document, it doesn't translate because of how this processor is bit addressed. So yeah, it's really difficult to understand, but if you're familiar with bit addressed processors, you'd get it right away. And I assume the reason why they did that is because it's a graphics processing unit, and you can address graphics bit by bit by bit in memory much easier, which makes sense because you can think of 1 bit as 1 pixel. So 1 bit per pixel. In this case, it's using a 256 color indexing system, which is not even 256 color. It's actually 16 color, but that was the other reason why it couldn't run 4000 based software, is because it was limited to 16 colors on version 1. Version 2, they fixed that, but they didn't expand the capabilities. But version 1 has got a 16 color system, and it's bit addressable. So they can buy a full address, like 4000, you can target the first bit. 4016, you can target the next bit, or the 16th bit. You know, something like that. Plus, there was a size operator opcode, so you can, when you're doing memory moves, bit blit operations, you can define memory sizes and all that stuff. This is all internal to that chip. Anyway, so they use this as a host processor. These 2 chips here are the address decoding network that defines where everything else is on the bus. Okay? Those are your 2 ROMs. This thing is not like the 4000. It doesn't have to download anything from the satellite to get it to run. All of the software for this machine is in those ROMs. And from what I can tell, I'm pretty sure that the 4000's original software was just ported over to this one and then compiled against this target. And when I say original software, when the 4000 was debuted, it debuted in a 3000 format. Okay? It did not have graphics modes, with the exception of radar. Everything else was all text-based, just like the 3000 was. This was based off of that software, so it's just targeted to a different machine. And it has a different C runtime when it was compiled for this machine. And yeah, this was compiled C because the thing about C code, when you're disassembling on processors like this, especially the 68K, C loves to abuse the stack pointer, and if you see tons and tons and tons of stack operations, chances are it was compiled C. That's usually how you can tell. And this is no exception. So these are the system ROMs, contains all the fonts. This thing actually has 8 fonts. I borrowed some of them to go over to the 4000. So the recreation of the 4000 software, the fonts you see on screen, they look so realistic because, well, they are. This has the same font package. Well, it has most of the same fonts. There are some very, very slight differences, but you really got to be looking for them. And I think they did that on purpose so someone at TWC could look at the screen and know which generation star it was just by looking at the screen, because they would ever so slightly, as like an Easter egg, they took the same exact font package and they ran them across multiple units. And that font package, they would tweak the W's ever so slightly so you know if it came from a Junior or a 4000. But the rest of the letters were identical, with the exception of the capital and the lowercase w's. So they would modify those. And the only thing I can think of is because W is weather. and they were a weather channel. So they figured, oh, well, let's just Easter egg the W's ever so slightly so you know if it's a Junior or a 4000 or a 3000. Well, the 3000 has a completely different font package, but anyways, so that's what they did. So I backported that and then modified the W's so that they look correct for the era. Anyway, so the fonts are stored in here in bitmap format. Drop shadows are stored with it. The font tables can be with and without drop shadows, but they both have outlines, and the outlines are calculated by the vector rendering routines in ROM. Anyway, so these are the buffers. 74, 373. They're probably latches and buffers. If I'm not mistaken, this processor has a multiplexed address data bus, very similar to that of Intel. So this has to demultiplex all of that. So now you got the main SRAM, which is backed up by this supercapacitor. We have the ROM. We have the address decoding network. We get over here. We have the dual UART. So this not only controls the RS-232 port, which is this is a dual function port. Primary function is to connect to a terminal, so you can get in here and set the addressing switches, is what they call switches, but the 3000 had physical switches on the front, rotary switches. They're electronically stored in an EEPROM right here. So the switches are digital, but they're still technically called switches, and this is how you set those, is from that point there. And you can get into various test modes and other things like that, but the alternate use for that port is for a sensor pack. I don't know the protocol, but you can plug a sensor control board in there, and this would use local weather sensors on site. The predetermined text format of the sensors is stored in the ROM, so I know this machine is capable of doing so. So, and the second UART is actually used for this EEPROM. So this not only talks to the primary serial port, but it also talks to this EEPROM somehow. They're using it for a bitbang operation. This is the video memory, and it's dual port. Unlike the 4000, this has got two ports, so it can be talked to by the CPU. At the same time, this gen locking circuit can read it out. And that's the job of this CPLD over here. This CPLD is what reads out pixel by pixel and what shows onto the video display. And the newer design, see, this one here has a TMS 34070. That's the RAM DAC. It's kind of like a RAM DAC, but sort of. That is what generates the graphics, on-screen graphics that go out. The newer machines, the version 2, they got rid of that chip and they replaced it with a secondary CPLD. My thought is, since both machines have the same firmware, that CPLD does some kind of logic translation, so this doesn't have to change. So it's still the same. But it's got an additional chip, and it's got a standard Analog Devices 256 color RAM DAC. Nothing special. So that chip serves as a logic translation to make it emulate one like that. And as I said, this manipulates the frame buffer. This is also responsible for the on-screen crawls, switching between pages and stuff like that. That's all done by this chip, because this can actually rotate the pointer that's being displayed on the screen. And there's the 4040 counter that does so. The rest of this circuit here, this is the NTSC encoder, which you'll notice something very similar, because that is the exact same circuit that is in the 4000. So that kind of makes me wonder if the engineers didn't cross, because the 4000 was apparently not engineered by Wegener, but this one is. So I'm curious if Wegener and Applied Microelectronics, or Nortel, was collaborating at one time, or TWC gave them documentation to the 4000 to create this unit, because this unit came after the 4000. This came out in the mid-90s. This one was, let's see, when was this made? Same serial number as the front. Yeah, 94, 93. I don't know if there's any date codes on the board anywheres. Anyway, so that's the NTSC encoder. These are voltage regulators for all the different analog electronics in this stage. And we have everything necessary for gen locking here. Like we've got LM1881 sync separators. The PLL's over here. Which actually, that's not the PLL, that's the main oscillator. It looks like, because there's the crystal. So we're going to have a burst lock. Like there's, I think that's one of the PLLs or something like that. And actually, no, I believe that's the analog mux. This is controlled from this guy. This is responsible for switching between a video pixel or a computer pixel. So each pixel, according to the pixel clock, this is the mux. So this will switch between the graphics that's stored in memory or the video that's coming in. And in order to do that, you need the pixel clock, and that pixel clock has to be gen locked with the reference signal. And the gen locking stage is up in here. There's some more muxes to do some more crazy things. 1496, I think that might be the PLL. And that's the analog mux. This chip here, you can tell where it's been resoldered on before, so that's a factory repair. So that's basically the video stage in a nutshell, and these machines are fairly simple. So we get over here to this stage over here. That's the radio. That's the receiver. And there's the IC that's responsible for detecting the incoming subcarrier frequency, the NE614. This runs on a 7.38 megahertz subcarrier, which is above video. So you got, if you're looking at a spectrograph of an analog video signal, you got your first 6 megahertz, which has got your audio and your video subcarriers from on your standard NTSC style stuff. Well, most televisions only go up to 6 megahertz. You use 6 megahertz of bandwidth because your sound is in there. Well, this sits just above the 6 megahertz. This on a satellite subcarrier, or a satellite transponder, which was actually the specifications that Wegener designed. You can have multiple subcarriers up to like 20 megahertz, 25 megahertz. I forget how much bandwidth an analog transponder has, but you can have multiple subcarriers that are just above the main carrier. And 7.38 megahertz was one of them. That is the same subcarrier that the 3000 used as well. So this locks onto the subcarrier and produces a signal that comes over here to the subcarrier alarm. If the PLL is not locked, meaning there's no incoming reference signal, this light comes on. As soon as it senses a carrier, no matter if it's FSK modulator or if it's just a plain frequency, it can be a sine wave, at 7.38 megahertz, this light will go off. And that's controlled by this chip. There's actually a pin on this chip that goes all the way down to an op amp that drives this LED. So then it comes out of there, and these jumpers will select how and why and where the demodulation occurs, because you can actually move these jumpers around, and you can pass the signal straight into this chip going away from the radio. So this can be a straight digital signal, an NRZ, non-return to zero encoded signal. So, but in this case it's not. So this radio picks it up, and then these two chips here are the integrator demodulator for the FSK. Okay, this demodulates the marked space frequencies coming from the satellite, from the encoder at TWC-HQ, that gets multiplexed onto the satellite into digital ones and zeros. Well, those ones and zeros these have a positive and negative voltage, and this is only on 5 volts. This is the CPLD responsible for decoding the ones and zeros from the data stream. And this is the reference clock oscillator, which is kind of weird. It uses this 3.9 megahertz crystal, and this is the PLL, some kind of a digital PLL to demodulate the signal for in there. So because this is 5 volts and this is plus minus 12 volts, the output, this is the output from the FSK mod, comes up and into these chips here, which those chips are acting as level shifters, not only for the serial port, but one of these gates is acting as a level shifter for the video, or for not the video, I'm sorry, for the data going into there. And then there's data enable, and there's some, different clock polarities and things like that. This is the FIFO right and FIFO out. So then This is the FIFO. So what happens is, as the frame is coming in, and the way this works is it works on standard teletext frames. It's modified. There's a patent out on this. You can look it up and see it all in the patent. And it's actually more complicated than the patent explains, which is what took reverse engineering efforts to figure out. But if you look at the patent, you can physically see that of how their teletext frames are structured. So there's the teletext frame, the framing code, the header, framing code, all that stuff. That comes in, and the raw data gets demodulated by this IC, it gets decoded, and the byte code gets dumped into this FIFO, okay? Well, every time a byte comes in and gets demodulated, you can watch that trigger signal right here with that test point. And then the output goes straight to the CPU. So the CPU gets an interrupt. There's an interrupt connected. So as soon as this thing gets a byte dumped into it, it fires an interrupt. So this thing will go off and read out the teletext data from the FIFO. So you don't need this whole subcarrier thing. You can actually remove this chip here and connect directly into the FIFO and dump the teletext frames straight into that chip to run this unit. And matter of fact, in the very beginning, that's what we did, because this chip hides some complexity that is not exactly straightforward. So, and here's the thing. So that's how that works. Now, the problem is the same data that goes in here is actually not the same data that comes in here. This chip has a built-in hardware cipher. So not only did they switch from vertical blanking to subcarrier, they also scrambled the signal. They encrypted the signal, and you can't talk to this chip directly. So if I send the frame in here with FSK modulation, that would be the same as in there, it won't do anything. You might get a flicker of the data light, but the reality is you won't get any data. And it took me a long time to figure that out, because the first thing I had to figure out was I had to figure out the baud rate, which luckily I did, because after I did the math from here to here and some other little things, I figured out the baud rate. I had a couple of guesses anyways. And even when transmitting at that baud rate, I couldn't talk to the CPU. It just wouldn't work. But if I went direct, I soldered to the underside of this chip, I pulled that chip, and I talked directly to the FIFO from the Arduino, it worked fine. I could fill up the screen and everything would work great. So it's kind of like, really? Anyways, so that's why I had to get 3000, because I had a hunch that this worked on the same data feed as the 3000 did, and I was right. The 3000 has all discrete logic, which I will get to the 3000 in another video. That has all discrete logic, and the hardware cipher is in the logic. So I was able to reverse engineer the cipher, and then I implemented that cipher in software, and then I modified the Arduino code that modulates my radio, the encoder routine, and it worked. Then I had full data. There's some other things I had to do, because you got to bias the line so you get the proper FSK demod and things like that, but that's more complicated than I want to get into. But once I figured out the hardware cipher, it worked fine. So then I was able to get data in there. So this hides a lot of complexity, and that's the problem going forward, is like, how do you get the logic out of that chip? You'd have to decap it for one so you can read the bit stream, but the bit stream is only half the battle. You got to figure out what logic that maps into, which means you have to reverse engineer that IC directly. It's not an easy task. Same thing over here. So, for example, if that CPLD loses its firmware or goes bad, this unit's junk, because you'd have to replicate that function. And that's going to be a problem going forward, trying to preserve these machines and keep them running. Anyway, so that is the FSK data coming in, gets demodulated by here into zeros and ones, which comes over here. This demodulates it to NRZ. The NRZ data goes in here, and this decodes it even further, decodes the cipher, and then it goes into the FIFO. And that's how it works. And everything's hunky-dory. Over here is the logic switches. And not entirely sure what TWC used them all for. I know they used one for pre-roll, which in the old videotape days, that would get your local head-end commercials ready. So this would light up before the commercial was called. So that way the video drum could speed up on the tape machine and get the tape queued. And then that's what one of these logic switches do. And the second logic switch starts the tape. And then after that pre-roll, that commercial's done, it turns them off. So that was commanded by the satellite. And also, there's a warning tone signal in here. So if this thing gets an alert, like if this thing gets a severe thunderstorm warning or a tornado warning targeted for the area that this thing is programmed for, that will trip. And it'll signal the alert generator, which injects audio into the signal going out of the head end to, your television. So all those beep, beep, beeps were generated by a tone generator that this thing connects to. The 4000, all that stuff was internal. And same thing with the 3000. The 3000 can actually switch audio channels and things like that. But this was the small little thing. That's why it's called the Junior. So anyways, that's it for this device. I'm going to actually plug this thing in and fire it up and show you how this actually works. Finding all the RCA cables and everything to hook this mess up is definitely something else. And then some of these cables are shot. Anyways, so for now, what I'm going to do is I'm going to plug in this unit, and we should watch it start up as soon as I plug it in. If I can do it one-handed. There we go. And there's the default screen that these machines produce when there's no data, no signal, no anything. Subcarrier alarm is on, which I expect because there's no, the modulator's not turned on. All that stuff is exactly as normal. So what I want to do is I want to plug the video stream in here, which this goes to my Raspberry Pi. So it should detect my Pi signal, I hope. Maybe. Or not. Really? Of course everything goes wrong when I'm filming. Why wouldn't it? Alright, there we go. Yeah, that's my cables are shot. Anyways, haven't probably used these in 15 years. So that's my Raspberry Pi coming from the time-base corrector, which is over there. Now, video light's on. So, in theory, as soon as I plug my modulators, this is my FSK encoder. This is the board that does the FSK modulation, which is just a simple DDS. But the encoding happens on this board. Because the problem with... I can't use the standard SPI, because the problem with SPI is you can only send 8 bits at a time. It sends 8 bits, processor's got to stop and send the next 8 bits, stop, send the next 8 bits, right? This runs at a consistent clock. There is no start and stop bits. So you can't just, send 8 bits, stop for a second, send the next 8 bits, because that time gap will throw everything off. Because the encryption is also based off the timing of this clock. It's very critical, so that means my entire 37-byte packet has to be in the FIFO and clocked out consistency, bit by bit by bit by bit by bit, without any stop gaps in between. I can have a stop gap between packets, but not between bits. So I don't know how to get SPI or serial port to do that or anything like that, because there is no... It's not asynchronous. There's no start bit. There's no parity bit. There's no stop bit. It's just digital bits. That's it. So, encoding happens on this board. Everything happens on this board. Gets transmitted out. The video signal is going through the board, because the thing about these Juniors is it's not 100% subcarrier. The data's in the subcarrier, yes. But there's a clock signal that has to be injected into the VBI. Without that signal, this thing gets confused and it throws all kinds of graphical glitches. But so that board there injects a clock signal at the correct VBI line. So the clock signal from that, this CPU references somehow. I don't know why it's that way. Probably because of the way the 3000 was originally designed. But with the 3000, I didn't have to worry about that. It was really this Junior that is the biggest problem. So that injects the proper clock signal into the VBI period, and which is also the subcarrier. The time, so the clock signal that is injected in here is also in phase with the subcarrier that's coming in. So, yeah. Anyways, it's a mess. It's amazing I figured any of this out. So I got to plug that in, and in theory, this is designed, because it's not just me that worked on this. There's a couple of other people that helped make this project happen. This converts the Junior into an IoT device, so that connects back to a data server over MQTT. So in theory, the minute I plug this thing up, I should get data, and I should get an LDL that pops up with the data on it once it's powered on. The trouble is going to be, what am I going to use to power this thing with? Because I don't know. Maybe I can use this cable if it'll reach, because I need a power source. And the cleverness of this uses an Ethernet shield, by the way. I'm sure there's newer systems you can use ESP8266s, but the trouble with that is I need full GPIO for the FIFO. This is a parallel 16-bit parallel FIFO, so I can't just use, because ESP8266 don't have a good enough thing. Plus timing, like I said, timing is key. Okay, power. Hey, we're energized. So that means, in theory, there it goes. Data light. It's on. So now this thing is pushing out a subcarrier. This thing, oh, I'm getting data. There we are. Here comes the data from the server. Now, I did not get current conditions data. Probably because I think there's a web portal that you log into to control these things. So I think it's set up for the 3000 and not this unit here. So, but then again, it did give me a unit address light. So, yeah, these things are finicky. And there goes the internet connection. Here's the way this system is designed. Since this is a single core CPU, if it locks up and unable to receive the signal from the server for some reason, or if the internet goes down, which the internet here is absolutely terrible, which is why I don't live stream or anything, I lose signal. So it goes away. It looks like it's pulling in data from the servers. It was. So yeah, that's how it works. So we got a subcarrier coming in. We have a data light now lit because this thing replays the same packet over and over and over again to keep this lit, because if this goes out, this will trigger into no data mode. Because watch what happens when I pull the plug. Boom. See? So you constantly have to have data going to it, or it won't work any other way. And it takes a minute before it starts seeing data too. And again, my RCA cables are crap, because these are from like 1942. There it goes. And there it is. There's the default LDL. But there's no data on the LDL, probably because my switches aren't correct. Anyways, that will do it for this video. I think I'm going to make the alert generator a separate video, which would be a really short one because there's not much to it. But anyways, this is how the Junior works currently, and thank you for watching. If you have a comment, please feel free to leave one. That's exactly what it was. It was the switch information. See, now I have data. You see, the thing is, these units are addressed, so in order to address them, you got to use a keyboard and get your switch information. So I had to pull up this old keyboard and do that.